Korepin from Stony Brook. Okay, he's going to talk about lessons on many-body quantum mechanics for circuit design. Please, Vladimir.
Okay, thank you for inviting me.
You
Actually,
changed the title of
I
the
changed the
talk.
title. I
Oh,
changed the title.
okay, okay.
A-
So,
And the topic is completely different.
okay.
So
It's not only
I,
the title. Okay, okay,
I changed
perfect.
I changed the title and changed the topic. It's actually high energy physics. So
Okay,
we're talking about nuclear physics, high energy physics, quantum field theory, and accelerator physics. Actually, we'll be talking about accelerator physics. It's called entanglement entropy production deep inelastic scattering. I will explain what it is. So
thank you.
first, uh so conference is devoted to Landau, Lev Landau. So Landau made important contribution also to high energy physics, not only to condensed matter. And here, Landau has a large school, a large team, which is called Landau School. Um, there are many students. There were many students. Some of them got Nobel Prizes, including himself. I'll be talking today my contribution of Pomeranchuk. Pomeranchuk was important member of Landau team. He built up a high energy institute in Moscow, ITAP, Institute for Experimental Theoretical Physics. And actually, there is a particle named after him called Pomeron. So this Pomeron, I will be talking about it. So let's start with accelerator physics, big machines, accelerator. So important process in acceleration physics is called DIS, DIS, deep inelastic scattering. DIS, deep inelastic scattering. So what is it? It's also called X-ray of the proton. So okay, so let me explain. So high energy electron, very high energy. This is like accelerators. So it emits a photon. Photon is on the picture, gamma, and then it's has very high energy and very small size. So the size of this proton, about this photon, gamma prime, the size of the photon is much smaller than the proton. As soon as this photon hits the proton, inside of the proton, it decays in a quark anti-quark pair, which is up here. There's a virtual quark anti-quark pair. But in the proton, there is already constituent quarks, which are below. So this start interact. The wiggly line is gluons. Gluons. So virtual quarks and constituent quarks, they exchange gluons, and this is the interaction between virtual quarks and the constituent quark. So, but gluons, these gluons, wiggly lines, they interact between themselves. And this interaction of the gluons is the center of my lecture today, because the interaction can be described by integrable spin chain. The spin chain interacts, described by beta ansatz, and I will be talking about this. So, on the other hand, in the end of the lecture, we should remember that this process has a finite time duration. It's called Joffe time. Joffe is a physicist, was a physicist. Then after it's like femtoseconds. After this process is over, each quarks start hadronization. Hadronization means that quarks turn into jet of particles, jet of elementary particles, which are detected by detectors. And those detectors, it's like traces of detect signals in detectors. They record it and then later analyzed by computers. And later, this take many years. And then later they compare it with the theory, which is quantum thermodynamics. So this will be subject BFKL. This were four people: Balitsky, Fadin, Kuraev, Lipatov, and these guys they sum up Feynman diagrams which describe this interaction of the gluon, and they discover the spin chain, which describe interaction of the gluons. And gluons once again. Well, anyway, let's move. So the whole there is important variable in this accelerator physics called Bjorken X. So Bjorken X, Bjorken was a physicist. Q square is momentum. Q is a momentum of this photon of this gamma, which is supposed to be very large. In theory, it goes to infinity, but in practice, it's as large as accelerator can afford. P capital is the momentum of the proton which were hit. and q actually my q is minus q minus my q small is minus q capital. So in the main, I have a scalar product of the momentum of the proton and momentum of this virtual photon gamma prime. So this is Bjorken X, and it's like central variable. Everything below we shall discuss scaling with respect to this Bjorken X. For this process, deep inelastic scattering, Bjorken X is the central variable. So the physical meaning of this Bjorken X is a fraction of the nucleon momentum carried by parton. Parton is a gluon in this case. Also, sometimes parton can be a quark, but here it's a proton by now. So by now, our main attention will be concentrated for small x. For small x, there is some kind of a scaling with respect to this Bjorken X, and then we'll be concentrated on this scaling. So let's some results which was known in the literature, actually because of Pomeranchuk. He was a student of Landau. So gluon structure function, I will explain what it is on the next transparency. So this, okay, let's come back. So this quark anti-quark pair exchanged by the gluons, I have to sum up with respect to different gluons. And Pomeranchuk was the first who take into account the exchange by two gluons, and this process called Pomeron. So let's see what come out if I take into account only exchange by two gluons. Then the gluon structure function, which I'll explain in the next transparency, scales with respect to Bjorken X, x raised in the power delta. And delta is a g square, which is coupling constant QCD. This is number of colors, 2 log 2. So this is some result. Later in my lecture, we shall take into account exchange of three gluons and all gluons. But it doesn't go to infinity because this process, the whole process exists only finite time, this Joffe time, but I'll explain later. So this is something which was known in the literature, and this is like our beacon. We go this direction, try to calculate corrections to delta. So what is gluon structure function, which was in the previous? Gluon structure function tell us how, which is the portion, what's the portion of the momentum carried by the gluons. I mean, the proton has momentum distributed among the partons, quark and gluon sitting inside, and gluon structure function tells us how momentum of the proton is distributed among gluons. So what's the portion of the momentum belongs to the gluon? This is important variable. It can be measured, as I said, indirectly, but it can be measured on accelerators. And this will be our main point of concentration, gluon structure, how gluon structure function scales with respect to the Bjorken X. That will be the point of my lecture. Now, this was what I said was introduction in accelerator physics. So, you know, I introduced main ideas, main variables. Now, the other part of my lecture is Beta-ansatz. I realize that right now in this conference there are many experts in Beta-ansatz, but I still repeat, make some kind of introduction because of the notation. I have maybe different notation that people get used to, and also my own point of view. So for a while, we'll forget this accelerator physics. We put this in the random access memory, and we concentrate on Beta-ansatz. Now, introduction to Beta-ansatz, and then they will come together. So Beta-ansatz can be, we can, you know, it's related to Young-Baxter equation. Young-Baxter equation, most famous spin chain, which was solved by Beta-ansatz, is XXX Heisenberg. So this is very famous. Everybody know how to solve it. I know all the experts here. So, but I use the language which by now kind of matrix product state. If I want to represent Beta-ansatz, algebraic Beta-ansatz and quantum inverse scattering method in terms of matrix product state, I will need L operator. L operator is the matrix 2 by 2. This is matrix 2 by 2 in the auxiliary space, which is virtual space on the language of matrix product state. And matrix elements are Pauli matrices. Those are interacting dynamical variables, and lambda, which is spectral parameter. And this is a famous, people call it intertwining relations, or This is just basically Young-Baxter relation. Our matrix by itself is 4 by 4. Lambda and mu are spectral parameters. I square root of -1. This identical matrix is 4 by 4. This is P permutation, which is 4 by 4. This is famous R matrix of the XXX spin 1/2. And it was solved by Hans Bird in 1932, and then later was reformulated in algebraic beta ansatz, which I think everybody knows in this room. So let's mention other model. So of course there are many other exactly solvable models except of spin 1/2. Another model we shall be concentrating called lattice nonlinear Schrödinger, but it has many names. Most famous name is Lieb-Liniger model, Lieb-Liniger model or Girardot. But I will need lattice formulation of this nonlinear Schrödinger. So it's kind of a Lieb-Liniger on a lattice. So delta is a lattice step here, a lambda spectral parameter. Kappa is a Bose field. It's like harmonic oscillator. Harmonic oscillator, and those commutational relations, starting commutational relation for the scalar field. Delta is the latest step. This is Kronecker delta, so it's equal to 1 when I equal j equal to L and 0 otherwise. Rho, which appears here, is the square root of 1 plus kappa. Kappa is coupling constant for nonlinear Schrödinger, and this is side against side. Okay, so this is a nonlinear Schrödinger, or latest version of Lieb-Liniger. It has a Hamiltonian because it's on the lattice and it's exactly solvable on the lattice. That the Hamiltonian is relatively complicated. It's in the bottom. So psi is actually a logarithmic derivative of gamma function, and j is a maybe just make it smaller. Okay, make it. Okay, maybe it will be on the next transparency. J is some square root of the scalar product of two spins in the neighboring lattice sites. It will appear later again. So far we're talking about beta ansatz. I mentioned two different solvable models, XXX spin 1/2 and nonlinear Schrödinger. So they're related. They have the same R matrix, 4 by 4, this the one which I mentioned, and the XXX L operator is equal to the proportional to L operator of lattice nonlinear Schrödinger multiplied by the Pauli matrix. And this XXX Hamiltonian I can also write as a spectral parameter. This is 3 Pauli matrices, and S is spin. But of this, so lattice nonlinear Schrödinger is also equivalent to XXX, but XXX with some other spin. It's not spin 1/2. Spin is actually -2 divided by kappa lambda. So of course it's not integer, not half integer, but we have infinite dimensional representation. So for infinite dimensional representation for C2, we can have a spin which is an arbitrary real number, including negative. Actually, we mainly will be interested in spin -1. So XXX L operator for this, by now we generalize from spin 1/2 to spin -1. Still looks like similar to spin 1/2, but representation of the spin is given in terms of the scalar Bose field, which is a harmonic oscillator. And by the way, this is Hamiltonian, so psi is logarithmic derivative of gamma function, and j is a solution of this quadratic equation. But in this quadratic equation, everything can use. So I can use standard formula, Viet formula for solution of quadratic equation. So I'll get some expression with the square root, put this inside of the gamma function. So this is Hamiltonian of what? Of lattice nonlinear Schrödinger, or I can say this is Hamiltonian of XXX with spin -1. Spin -1, and it is actually the interaction of those gluons which I mentioned in the beginning. So now we shall merge this beta ansatz together with dependent elastic scattering. So this is Hamiltonian, this BFKL Hamiltonian, Lipatov Hamiltonian of interaction of the gluons in dependent elastic scattering. So let's press it. So this model looks complicated, but beta ansatz solution is, especially algebraic beta ansatz, is very standard. It's actually very similar to spin 1/2. So usually the main result of beta ansatz is beta equations. Beta equation for lambdas. Lambdas are spectral parameter rapidities of the waves. So of course for XXX I'll say spin waves, but since I apply this to accelerator physics, I will say this is color waves going through the gluons. Color waves through the gluons, they have their own rapidity, and those lambdas are rapidity. Of course, I is square root of -1. L is uh, total length of the lattice, which will be kind of large. And n is number of the gluon exchange. So can be 2, Pomeranchuk, or can be more, and I have to sum up. So these models were solved. I mean, analyzed. These beta equations was analyzed in the standard way. How beta and that's usually analyzed, meaning that the thermodynamic limit it turns into a linear integral equation, and I get the ground state description. Also, in thermodynamic limit, there is no gap; it's gapless. So there is some CFT, conformal field theory, which describe low-lying excitations of this model, lattice nonlinear Schrödinger, or XXX with spin -1. So how I can calculate central charge of corresponding CFT? So the idea is to consider finite size corrections. So L, now I'm speaking the language of Betanzas. L is the length of the lattice, the volume. So energy of the ground state is proportional to the volume, to the length L with some density. And that is the correction. Corrections is 1 divided by L. I'm interested in this correction. There are further corrections, 1 divided by L square, but I'm interested only in 1 divided by L. So here I can calculate this, and the correction have this expression. V is the Fermi velocity. Fermi velocity is velocity of these sound waves, the color waves, the gluons. The coefficient here is very important because I can compare this with the standard CFT expression, conformal field theory. In conformal field theory, I have similar expression, but the coefficient should be C here, C, central charge. So comparing this expression with CFT, I conclude that central charge is equal to 1, which will be very important later. So far, I analyzed this beta ansatz of the model. So this was kind of an introduction to beta ansatz, which the model which appear, XXX with spin -1, it describes interaction of the gluons in my deep inelastic scattering. This model, XXX spin -1, also equivalent to lattice nonlinear Schrödinger with some specification of the coupling constant and lattice step. So let's return back to the beginning of our lecture, of this lecture. So we start with deep inelastic scattering. So remember this electron emitted photon, which carry momentum q. This is quark anti-quark pair. This is constitutive quark. Upper was virtual quark. And this is interacting gluons. The gluons arise as interaction between the quarks, but now we're interested in interaction of the gluons between themselves. So we shall need some new variable. I mean, I want to go through some history of discovery of this Hamiltonian of interaction of the gluons. So I will go a little bit through the papers of BFKL and Lipatov specifically. So in order to go through their papers, we need one extra variable, which is Z, complex variable. So this gluon has a momentum, Q, and we shall consider plane perpendicular to this momentum. And so we in three-dimensional space. So this is axis of momentum perpendicular to two-dimensional plane. So we will describe it by the complex variable Z. I mean, Lipatov did. So Z variable will appear. So BFKL, Balitsky, Fadin, Kuraev, Lipatov, they sum up Feynman diagram describing all of these processes which I described. And this is their expression for their Hamiltonian of the interaction of the gluons. So it's in here. So only nearest neighbors interact periodic boundary conditions. And the P capital in here is derivative with respect to this Z perpendicular variable, perpendicular to Q. And there is also Z with two indexes with difference of 2Z, and this is Euler coupling constant. So this is their Hamiltonian written in terms of log Z, this derivative, inverse derivative, and it looks gloomy. And also derivation was done a long time ago, but derivation is highly intuitive, so they have a very strong physical intuition, so difficult for me or for other normal person to follow. But nevertheless, we can do something with this Hamiltonian. We can rewrite this Hamiltonian in terms of SU2 generators, of SU2 group. So I can introduce, using their variables as Z, I can introduce SU2 generators, S plus, this is Z squared differentiation, S minus is S plus, S plus is minus is Z. So I can check that they satisfy SU2 commutation relation, and I can rewrite this Hamiltonian, BF-Kyle Hamiltonian, in terms of this S as of generators of SU2, and then I can change the representation of this SU2. Instead of the Z, I can consider my latest nonlinear Schrödinger, or XXX with spin minus one half, because Hamiltonian anyway is written in terms of S, and spin is equal to minus one. So I can just change the representation from differentiation with respect to Z to the one which I mentioned. So in here, L operator, which I mentioned, is two-dimensional in auxiliary space, but infinite dimensional in the quantum space. So there's another second R matrix which describes intertwining relation of these L operators. This is a second R matrix, which is a standard construction in quantum inverse scattering method. Gamma is gamma function, spectral parameter S, which is equal to minus one spin, and J is this thing's solution. J is in here, so J is the solution of this quadratic equation. So let's proceed with the analysis. So right now what we're doing, we're analyzing the Hamiltonian, which was derived by Lipatov, BF-Kyle Hamiltonian. So let's move. So this Hamiltonian, so now I am applying the technique of quantum inverse scattering method to the Hamiltonian of interaction of the gluons of BF-Kyle Hamiltonian. So I can write it as logarithmic derivative of this R matrix, of this gamma, which satisfies Yang-Baxter equation by itself. And I can get this Hamiltonian, which I mentioned earlier. So we're doing fine so far. So this is some historical reference. As I said, B.F. Kalle's derivation of this Hamiltonian is correct, but highly intuitive, and actually it's very complicated. So later, there was another derivation of this Hamiltonian. By derivation, I mean analysis of Feynman diagrams of quantum chromodynamics. Was done by Ronald Kirchner. He managed to use Yangian symmetry. Yangian is a infinite dimensional quantum group. And he rederived the same Hamiltonian. Hamiltonian didn't change, but derivation became much more clear. So if people interested in this derivation, I strongly recommend his paper. There is also a book about legacy of Lev Lipatov in Singapore, was published in Singapore. So anyway, let's come back. So we consider this Hamiltonian of Lipatov. We change representation to the standard XXX with spin of minus one half, and then it's equivalent to this latest nonlinear Schrödinger. Then after this, what we can do, we can describe the ground state and low-lying excitation of this XXX spin minus one. So we arrive to the conclusion that low-lying excitation can be described by CFT, conformal field theory, with central charge equal to 1. So what's the use of this spin chain? I mean, I want to calculate something which can be measured on accelerators. So beta ansatz, what it does for me, it's give the ground state some energy of excitation, but I want to calculate something. I want to describe my deep inelastic scattering. What about my photon gamma star, which was in the beginning? So maybe you remember my picture about this photon gamma star turning into pair of the quark anti-quark pair, and then there's a chain of these interacting gluons. So from the point of view of the gluon chain, the original photon is a quench. So I can apply the technique, modern technique for describing the quenches. I mean, majority of the people know this is cardiac collaboration, but there are many other people who worked on this. So this photon, right now I'm speaking different language. Now I'm speaking the language of beta ansatz, hit my gluon chain and they get excited. So the energy, entropy, entanglement entropy, start changing with time. So entropy increased logarithmically with time, and the coefficient central charge divided by 3, but I already calculated central charge. It is 1. So entropy is 1/3 log t plus some constant. So let's see what we can do with this entropy. Is this useful for calculation of gluon structure function? Remember, Pomeranchuk calculated gluon structure function for the exchange of the two gluons, and now we take into account all the gluons. So can we calculate gluon structure function using this entropy? We have to, well, in here I remind two things. First of all, we managed to calculate central charge, but also there is something which is called Joffe time. I will explain in a moment. What's Joffe time? Joffe was a physicist, Russian physicist. So the picture in the beginning, which I showed, where quark gluons appeared, describing interaction of the quark anti-quark pair with the constituent quarks, this lasts for a short time. It lasts for the Joffe time, and Joffe time denoted by tau here. It's one divided by mass. It's one divided by mass of the proton, and then this is important later. So let's move. What we can do with all of this? Now we can read the paper by Karchemsky, by Harziev and Levin. Harziev will be in São Paulo like in a month from now in other conference, also in São Paulo. So Harziev Levin, they describe, they were interested in the color singlet dipoles. This is quarks, which are like singlets, but singlets in relation to the color group. So S entropy, which we can calculate, is equal to the log of the number of the color singlets. Why we're interested in this? Because for small x, for Bjork and x, multiplicity of dipoles is given by gluon structure function. This is our main interest, so gluon structure function. So by now, well, and Joffe time. So Joffe time show how long this process lasts, the one which I'm solving by beta ansatz, because it lasts for short time. And then after this, quarks start turning into jets of elementary particles, and jets kind of detected by detectors. So Joffe time is important. The file, okay, so what we can do with this? So number of the current gluons, which Harziev and Levin can calculate, for small x, equal to the gluon structure function. This is x, gx is notation for the gluon structure function. And it is equal to the x entropy. X entropy depends on time, but for time, I should choose Joffe time. So entropy is simple. This is by minus 1/3 log t. Instead of time, I substitute this 1 divided by x. So I put all of this together, and I got my answer, which is gluon structure function for small x, scales as 1 divided by x raised to 1/3, power 1/3. This 1/3 is a big deal. Because in the beginning, for Miron, it was some function of the gluon coupling constant and number of the colors, but now we sum up with respect to gluons, we got 1/3. Okay, so this is actually a big deal. Why is big deal? Because this gluon structure function can be measured. So one need an accelerator for this. One accelerator existed in northern Germany. In northern Germany, they had accelerator which is called HERA. This is abbreviation, of course, HERA. It measured this deep inelastic scattering. Then it was decommissioned several years ago, but the data remains. The data from detectors were analyzed by brilliant physicists from Oxford University, Amanda Cooper-Sarkar, with co-authors, and they compared the analysis with QCD, with quantum chromodynamic. This, our 1/3 is in the range. It's in the range. So what we hope is that in the future, more accelerators will be built. Like in this Long Island, we building this electron ion collider, which will be active maybe in 10 years or more. And then for new accelerators, Q square will be larger, X will be smaller. So we hope for better confirmation of this 1/3. So once again, gluon structure function, which we described, shows which fraction of the momentum of the parton carried by the gluons. That's a more formal definition of the gluon structure. That's what we calculated for small x, scaling with respect to Bjork and x. Okay, so we're coming to the end of my lecture. So this was application of ideas of Lev Landau to modern accelerator physics. That's all I want to say. Thank you for your attention.
Thank you, Vladimir. Okay. Questions? Please. But you have to use the microphone.
No, it's a simple question. Your second R matrix, is it related to the Veneziano amplitude?
Okay, first of all, can I ask your name?
Yeah, your second R matrix. It looks like the Veneziano amplitude. Is there any relation with it?
You know, I'm trying to find the second R matrix. This is first R matrix. Okay.
Yeah, the second one is the ratio of gamma functions.
Yeah. I'm trying to find it. This one. Yeah. So we arrived at this formula analyzing Young-Baxter equation and the relation to with Nissan amplitude I didn't analyze, but maybe my lecture is possible relation to this. Maybe it's related. So I haven't thought about this. So if it's related, maybe you should pay more attention to that.
Yeah, because the Veneziano amplitude would be related to all these scattering we're talking about.
But
yeah.
I mean, you asked me a question, but what is your name?
My name, Luis Ferreira.
Okay, Luis. Marina, maybe people who ask questions, maybe they first say the name, so I know to whom I'm talking about. So this might be an interesting idea to analyze this relation, because somehow for us this was formal mathematical expression which came off Young-Baxter equation, but if it's directly related to Veneziana, this is interesting. So my file, by the way, is with organizing committee and also with Harzeev. We published with RefD. Also, Harzeev himself will be in São Paulo. So maybe we should think about this more. Thank you for the question.
Hi, Korepin. I am Herman Sierra.
Hi, Sierra.
Hello. Well,
Herman Sierra. Hi,
yes.
Herman.
Hi.
Good to see you. I don't see you, but good to meet you.
Okay, I see you in the corner.
Yeah.
Okay, a simple question. This algebra, SU2, believe it or not, we're not using SU11, I mean the non-compact version. You're using the compact version.
No. The algebra is still SU2. The representation is infinite dimensional. Representation is spin -1. The algebra is still SU2.
It's still SU2. Okay.
Yeah.
No, I was thinking
but
that.
Here usually when I give a lecture for physicists like in BNL, we have a fight because as SU2, everybody know representation is integer, half integer spin. But this is true only if I want to consider finite dimensional representation. Here I give up. I don't want finite dimensional representation. I want infinite dimensional representation. And then spin can be any real number, and including negative, I want -1. So it is SU2. Thanks for the question, Herman.
Okay, then you have the central charge C equal to 1.
The central charge equal to 1, it's often happened in beta-ansatz. Not for all beta-ansatz, but it's often happened for beta-ansatz. Many beta-ansatz solvable models have central charge equal to 1. Yes, what's your question?
Okay, no, then do you have the primary fields for this theory?
No, we didn't discover that. So maybe you should work on this. This is a good idea to push through. This definitely needs a development because this, what we get, the gluon structure function, 1 divided by cubic root of x, it has corrections. I mean, there is a whole Taylor series in this cubic root of x, and we need to calculate not only leading term, but corrections. And then in order to calculate corrections, maybe your primary field will be important. So it will be great if you look into this. I will be grateful to you. Please do that.
Okay. Well, thank you. Thank you.
Hi, Volodya. This is Dmitry from Natal. My first question is, I guess...
Melnikov?
Yeah, that's right. So my first question, I guess, is when are you coming to Natal? Because you skipped São Paulo, apparently.
Yeah. Definitely. We can discuss this and maybe another Zoom. So thank you for invitation. Definitely we shall discuss this.
Okay.
Thank you for your kind words and thank you for invitation.
Physics question. So when you discuss the entropy of the quench, so you compute an entropy of what exactly?
So let me come back. The entropy easier to describe if I think in terms of the beta-ansatz, in terms of my spin chain. So the picture which I had in mind, and also Cardi collaborator had in mind, is the following. We had ground state. Ground state doesn't depend on time. I can evolve with time. Ground state, nothing happens, just multiply by some phase. On the other hand, if I hit it with a quench, my photon came in. Then the new state, after it was perturbed by a quench by my photon, it's not the eigenvector of the Hamiltonian anymore. So this place local position, local website, which was hit by the photon, local gluon, it starts spreading interaction around. So there's some kind of a shock wave coming along the spin chain, which originated from the hit by original photon. And this carries some entropy. So this is entropy of the disturbance of the spin chain, which describe interaction of the photon. And disturbance, I mean, from my later point of view, disturbance can from the photon. So, I mean, Dmitry, in the classical case, this was zero temperature. But for the final temperature, this process was analyzed in 19th century by, I mean, I forgot the name, but some, I don't know, Gibbs or Boltzmann. So for them, what they consider atmosphere. And at that time, they already have explosion, dynamite, I mean, artillery shell. So artillery shell explode, there's a shock wave. It has a front, but inside of this front, the entropy density change. So the total change of entropy inside of the front is linear function in time for positive temperature, but for zero temperature, it's logarithmic. So Dmitry, this is the entropy of the disturbance which photon created in the spin chain. Did I answer your question?
So it's a particular gluon that is hit by the photon, right? You were just looking.
Yes, yes, okay. It's local in this. Yes, short answer is yes.
So I think it's also interesting to know, like, if you know how to compute corrections to this result. A nice result, by the way.
This is first, thank you very much. But correction will be interesting because what I do is leading approximation was a little rough. I mean, even the Bertus and that chain is not fully identical to the CFT because it's only low-lying excitation. But also in CFT, like Zamolodchikov constructs this perturbed CFT. So there is corrections, definitely, and they can be calculated. And once again, my answer for gluon structure function is not final answer. This is leading term of asymptotics for small x. There is a coefficient in front of this, there is a constant term, and then the squared cubic root of x plus square of that plus square. So correction should be calculated, and they're useful because they will give us more precise expression for gluon structure function. So I agree completely with your idea.
Thank you.
Thank you.
Okay, more questions? No? Okay, we thank again Vladimir. Thank you very much. Yes, thank you.
Bye-bye. So I disconnect by now. I hang up, correct?
Sorry?
I hang up, disconnect. Bye.
Yeah, bye-bye. Bye.